So, good afternoon, everyone. We're the 3D printed remote controlled aircraft group, and it's our presentation on the first semester. I see you walk up for you. So to start off, the requirements of this project was it needed to be largely 3D printable, remote controlled using outsourced components. The wingspan need to be less than 0.5 meters, and the plane needs to achieve a speed of 70 miles per hour and remain in flight for 20 minutes. So we took these requirements and digested them a little bit, and that led into our preliminary research for the semester, just overall, how the heck is the plane going to be able to accomplish this, and then moving into designing specific components like the control surfaces, the fuselage, the wings, etc. So those got partitioned out after we did some initial research.
So one of the things we researched was different tail designs. Did a lot of research into different aerodynamic shapes and kind of came to the conclusion that with the rear section of the plane and the controls, it would be best to use a teardrop shaped design on most of the pieces. So that's kind of what we started here with the fuselage, and then also implemented that design into the control surfaces themselves. Starting with a swept design, which I'll talk about here in a second, we set up kind of an initial span and chord length based on the wingspan. So the span of the control surfaces is 1/3 of the span of the wings, and the span of the chord length of the control surfaces is 1/3 of that. So those were initial calculations we found from different references that we found both in the library and online for RC aircraft. And the other thing that we kind of adjusted through the process was this length of the fuselage, which I'll talk about here in a second as well. These are the two designs we ended up coming up with. We have like a swept design, like you see on a lot of modern aircraft, like your 747s and whatnot. And then there's this kind of a more antiquated design, but from the research we found online for our Reynolds numbers, it was going to be more aerodynamically efficient at the speeds we're going. So that was another one we decided to consider. We ended up doing drag testing on both of them, which I'll also talk about. But one thing that I made sure to set up when we designed these was they both have the same span. This has a set chord length, but this one has a slightly differing chord length. And the reason I set up the chord length a little different on this one was to make sure the wetted area would stay the same. And then we also kept the thicknesses the same for testing so we could compare the two designs to see which one would end up being more efficient. So we also experimented with these wall thicknesses some, which you'll see later with the fuselage as well. And one thing we noticed was we were originally going to go for 2 millimeter thick walls, which would have provided more than enough strength for the aircraft, but it makes it excruciatingly heavy after it comes out, and it kind of gets to be too heavy for our wingspan. And so we've moved down to 1 millimeter thick walls to kind of account for that weight savings. So this is some of the initial CFD we did. We did CFD on both of these designs at 70 miles an hour. I put blunt bodies on of them so we could confirm them versus the wind tunnel testing. And as you can see, the drag on the swept surfaces was found to be lower than the drag on the elliptical surfaces. Also, this enclosure we designed is made to mirror the Greenheck wind tunnel in the basement of Steel 1.
And so we also wanted to do some research with the fuselage, get some basic ideas. But before we needed to do that, we quickly realized that we needed to do some research into the components. And when it says research components, that's more actually research for the fuselage itself, seeing as the fuselage itself kind of was going to be built around these components. In terms of the motor, when we were looking at all the different motors online as we were going to purchase them, we were looking to maximize the KV rating, which is almost almost a metric of how much power the motor can max produce. We were looking to minimize the size and weight, considering how tiny this aircraft was. A motor that was like 5 pounds was not going to be viable. And then, most importantly, we're also looking to keep within the budget. We were looking online and looking at all these different sites and suppliers. Some of the motors, they got up to like $400, $500, and that's just not within the scale of this project, even if they would have been amazing and perfect. continuing off of the motor, we were looking at the propeller, and this was entirely based off our wingspan, actually. As the wingspan, we had a given number of 0.5 meters. And when you look at, based on the research we did, when you look at the blade diameter of these propellers, they should roughly be around a quarter of your entire wingspan. And given a wingspan of 0.5 meters, we converted that to, like, that's close to 20 inches, and a quarter of that, 4.92 is what we have specifically based off of that meters, but then we upsized it for practical reasons, since 4.92 is a little bit hard to find on some of the suppliers. We also looked at into using different amount of blades on the propeller themselves. 2 versus 3 is what we have currently. And we purchased these just to see once we had our motor itself, so that we could kind of see actual efficiency and how this would affect our craft itself. And then finally, going back to like kind of how I talked about the budget when it comes to the motor. When it comes to the propellers, we were under the assumption that the propellers are going to be the first thing to break if anything happens during testing, during flight. The propellers are going to be on the front of the plane, they're going to snap. So this is why we decided to even go with buying propellers online instead of 3D printing them, is that we wanted to be able to purchase a ton of them just so that we can test them. And then also so that when we don't have to actually design the propeller themselves, have the 3D printer have these really complex aerodynamic curves and like lofts and all that. And we just figured it'd be a lot easier and cheaper just to buy a couple of them online. When it comes to some of the other components that we've looked at over this semester, we looked at an electronic speed controller, which is going to be controlling our motor, controlling our electronics, basically. This was based on our motor requirements. The motor online, when we looked at the supplier and the specifications of our motor, required a 40 to 50 amp ESC, and we went with a 50 amp just on the safe side, and it was also what was available. And finally, for the transfer and receiver, this was actually based on prior experience Carson has had, so I'm actually going to let him talk about it.
Yeah, so we ended up picking a FlySky i6X receiver. It fit well within our budget. It was only like $60, so it was easier to get at. And it has 6 channels and different iBus and SBus programs in it for telemetry and stuff like that. So it was just a really, I've had some experience with RC airplanes, so it was a good choice to fit within our budget and get what we needed.
And then going back to now that we have all these components, now it's actually time to look at and research different shapes and all the stuff for the actual body and fuselage itself. However, as I kind of alluded to before, the research and development was kind of guided based on, well, one, the wingspan, but also just practicality, and then based on other designs and research, all the other research we've done. I started off with like looking at nose cone. This was the very first thing I did. We've one type of stuff where always based on the motor size, and just I made multiple iterations to just match the body as we continued on. And in terms of the body itself, again, as I said, based on the size of the parts and our orientation, it'd be cool. And I looked into different like air teardrop designs and stuff, but there was just some practical considerations where I have to fit the motor, I have to fit the battery, I have to fit all this and have them snug and secure. And then also based on just tail and wing research that we did as a group, and accessibility in terms of just being able to make the thing.
So then for the wings, we had the span length and chord were researched, and we were given that the max size could be the 0.5 meter. And we determined that we want to try and use as much of that room as possible. So those just 0.5 meters minus the fuselage diameter, which, as Liam was talking about, that diameter was chosen based off the largest size of the internal electrical components. And then also researched the chord length and how it can be modified to either make the plane more stable or generate a higher amount of lift. So we went through multiple versions of the actual wing design, which you'll see later on. Also researched the leading and trailing edge to see how the blunt versus sharp leading edge, which go with the blunt because it's going to subsonic speeds it'll be operating at, along with working on the trailing edge because of how it is set up. The tails fins are also right behind the wings, so we don't want to have too much boundary separation to form a wake. So the development of the wing was just a quick symmetrical airfoil, which was made because of the ease of CAD modeling. And then in this design, we were able to think about where we'll place the servos for the ailerons, along with also how we're going to mount it to the actual fuselage, and if any support structure was needed inside of the wing. This was then later modified in its second generation to be a non-symmetrical because they generate more lift compared to the symmetrical version, along with also design how the actual ailerons will be attached to the rest of the wing. So then the wing, we then decided to go with the non-symmetrical and further optimize it after running out of our tests. So we began running simulations on it through CFD and ROSI. And this actual shape for the airfoil was designed with the help of the NACA airfoil generator, which was the inspiration for the wing. And then the design was modified slightly in order to help out with the ease of 3D printing. And then the mounting arm, as you can see here, which goes inside of the fuselage system, was designed to have a tight tolerance, so it fits without needing any additional supports. You can see in that design, it had holes for screws, but due to the tolerancing, that is not necessary, but glue will still probably be added in order to add a safety factor. And then the wing was also determined to be shelved to the minimum size possible that the 3D printing nozzle allows in order to reduce the amount of weight, and that the internal structure at the lean edge would be able to support it. So then some FEA was done, analysis was done on the wing in order to determine how much deformation will happen while it's in flight. So we can see some of the assumptions that was made to the boundary conditions for, like, the air density was at the sea level and the mounting arm was just acting as a fixed support, with the hydrostatic pressure acting upon the leading edge at 1200 inch per second squared. And then this resulted in a total deformation of just a nearly negligible amount happening to the wing. So we realized that the internal structure added enough support that it wasn't much of a concern during flight. So further refinements, you can now see how the internal structure was designed and the actual CAD drawing of the wing. And so as I mentioned earlier, it was designed horizontal for ease of printing, but that wouldn't be the optimal way to actually attach it to the wing. So through CFD simulations, which we'll see later, the optimal angle of attack was determined to be at 5 degrees, which will be how it actually gets mounted. And as shown on the last slide, the internal structure was finalized and checked FEA to make sure that it would properly support the wing.
We also conducted fluid testing on the wing surface itself too. We conducted it at 3 different angles of attack just to see what kind of difference in lift we could gain from that. This is actually a half wing, so it's only one side of the plane, basically modeled in ANSYS Fluent. We made the same style enclosure of 1/2 meter by 1/2 meter, and then we tested lift and drag on this one wing. As you can see, the half wing just at 0 degrees angle of attack makes roughly 3.5 newtons of lift force, and is a drag force of 0.49 newtons. But just angling at 5 degrees on the fuselage would give us almost 7 newtons of lift, and only increase the drag by another 0.5 newton about. So, but then going up to 7 newtons, we realized that there wasn't much of a gain anymore. So we're thinking the optimal angle of attack for the swing on the plane would be 5 degrees, which is probably what we're going to move forward with.
And looking into the actual design of the fuselage, now that we've gone over some, like the wing, some of the wings and some of the other research, I started off with a pure cylinder design. This was just to get the kind of the length going, which is based on the wingspan, as I talked about before. The actual length of the fuselage, including the tail and the nose cone, it needs to be around 70% of our wingspan, leading to a total length of around 35 from tip to tip. I've worked with and modeled in SolidWorks multiple iterations, trying to work with all the internal components as we started to select them throughout the semester. And I designed the motor cap itself to not only have the motor, but to think about future connections when we're actually model them, whether it is with a screw or some other method that we have. Continuing forward, as you can see now at the top right, the design started to come a little bit together. This design now was based on actual dimensions now that some of the CFD and FEA for the wings and the tail structure were actually completed. And I've also further continued to modify the amount of space needed for connection points, the components as we continue to keep on selecting and researching into them. And then as Carson talked about back when he was talking about his tail structure, kind of lower that wall thickness to decrease our estimated weight and decrease our weight. And that leads us to now the current design, which is hidden under some duct tape, but is now in front of you. From just for the fuselage itself, from the tip of the nose cone all the way back to where the tail, the actual tail starts, it's 23 centimeters. The max diameter is 6 centimeters, and with the wall thickness that I talked about, 2 millimeters. And with this design, it was kind of taking what we had before and just being able to put it all together. There's additional space for and support for the wing connections, as you can see over here. Before, like if we took the wings and we put them together, it's like, oh, there's a gap. That's, well, we can't really have that. So we added in support and slots for those wings to slip in. We also split the fuselage in half. This was in order to have ease of access to electrical components and be able to move them around without having to dig our hands inside like a plastic tube. And then finally, this was, as you can see now, it's primarily designed for testing using ROSI, which I'll get into in a second here, and the physical wind tunnel in the basement. Speaking of ROSI testing, we used the virtual wind tunnel application for ROSI that was designed by Dr. Patterson. And we used it to test, get some initial drag and lift ideas, just to test it before we changed it for wind tunnel. And we were able to get 3 ROSI tests going, one for a full length wing design, one for the body, including the tail. And then once we got it all together and updated our designs to have everything fit and made together properly, we tested a complete prototype. And just going over some of these numbers, just so that some of the analysis and what we say later will make sense based on ROSI. The first thing to note is that the Reynolds numbers we calculated just using the density of air, our speed that we're putting it at the max at 70, the dynamic viscosity of air, and then depending on the part, overall length, and as far as we could, as big of an area as we can. And using this, just to take a look at some of the drag and lift forces, the full length wing has a drag force of around like 6 newtons, and the body and tail has a drag force of around 2.5. I guess you're almost rounding up to 3. And in terms of lift forces, the wing designs that we had at the time gave us a lift force of around 13.6 newtons, and the body and tail, they're not really providing any lift, but I added it just to have some comparison to the next thing, which is when we got the full prototype, we were able to look at, when we ran it through ROSI, our drag forces were at 8.05 newtons of force, which when you look at the wing and the body and tail before we optimize them, it ends up being pretty close to what we estimated. And then in terms of the lift forces that we were able to calculate, again, also a little bit lower, but in the general area of what we were finding with the wings before.
So moving from ROSI simulated testing to wind tunnel testing, like we alluded to earlier, here we have just one wing. What was ran in ROSI was the full wingspan of the wing. So to correlate that, you could double these numbers if you wanted to see better correlation. But what we did was we did a lift test in the physical wind tunnel. Then in the Johnson & Johnson Control Lab, we also did a drag test. So using the strain gauge data for the lift test, we're able to calculate lift values. And then using the weight measurements from the bottom test being attached to a slidable plate attached to a string that would just change it would just change the mass value as the speed increased in the wind tunnel. We took these findings after increasing the VFD drive in increments of 5 to come up with some data where you can see that the lift of the wings got to be around 4 newtons and the drag was around 1.4 at around 71 miles per hour. So the physical wind tunnel reflected some of the results a little bit. The numbers are smaller here than in Rosie, which we're looking to dig into why that is next semester. But the wings stayed very stable when me and Carson were watching them test. So we at least know they're very stable as they go through higher speeds.
So we also tested the control sections. We actually have the 2 models that we used right there. These have super thin walls. They're like 0.4, 0.8, 0.8 millimeters thick, just to reduce plastic. And one thing we were testing there was to see what the wall thickness, how thin we could go before it starts to become too thin. But anyways, we tested these in the wind tunnel the exact same way, 5 hertz each time, which is about 7 mile per hour increments, and mounted them using these surfaces at the back that you can see there. There's like a square block that we mounted on that sliding plate, which moved away, like Gavin was saying. And for that, we were seeing, for the swept design, we saw a little bit lower drag up at up above 60 miles an hour, but the elliptical design had a decent amount less drag below 60 miles an hour. So we're thinking in the future, we'll probably end up choosing the swept design just because it has the lower drag at the speeds that we would like to go.
So some other testing we did was on the thrust of the motor we bought because we were able to get some components in our hands this semester. So all we did was we tested the motor with the two blade prop and the 3-blade prop to see if either one would pull more thrust. We found that they drew similar amounts of current, and the 3-blade prop only had a slight bit more amount of thrust. So if what we found with that is we'll just choose which prop provides the more thrust at the end. And another thing Another thing we need to consider also is this is 358 grams of thrust. The current weight of our plane right now is resting at around 1100. So we're looking to cut into specific areas of the plane to reduce weight so that we can account for components being added on and other things, and then potentially looking at a motor that could give us more thrust than what we have right now, if that's what we need to do. And in summary, so what we found through this semester as we went through an iterative process to get to testing, because the ability to 3D print prototypes allowed us to test much faster than spending a lot of time making our CAD models perfect. We were able to test them a lot faster. So our current results of the plane before you and Rosie give us a lift drag ratio of 12.1 newtons to 8.1 newtons at around 73 miles per hour. So in the simulated wind tunnel, our proposed design is reaching project objectives. There is some criteria and refinements that need to be made next semester, but our current findings show we're on the right track. We did also, as the duct tape is there, we did it to test the full plane itself in a physical wind tunnel. That test became very shaky, and we very quickly found out the mount was not able to hold the plane very securely. We were able to get one data point and we correlated some of the things to get an assembled plane result. But when we come back next semester to be able to do better testing, we intend to fix how we're mounting the plane and along with reducing weight and other items.
Originally too, we mounted the plane in the back of that, in this square control surface like the other ones did in the wind tunnel too. And the mount that we had wasn't sufficient to hold the weight of the whole aircraft up. And as soon as it started to generate lift, the airplane went back and tried to rip itself off.
So seeing that, we're just noting to ourselves how we want to test it in the future. Other parts of the plane, the wings are actually very good. They showed significant resistance to deformation at high speeds. So the blunt area at the front is giving us a good lift drag ratio. One thing we want to explore is changing the angle of attack of the wings and plane, because currently on the structure, they're at about 0 degrees with previous results will probably move it to around 5. And yeah, that was how this semester went. We're looking to refine our design. Let's go correct structural integrity of the current design so that we can print, so we can print multiple prototypes for testing next semester. Do you have any questions?
Yes.
It's about productive.
I'll just ask a couple of them. So some of the constraints you have, it's gotta go 70 miles an hour, 20 minutes in the air, half-meter wingspan. Is that coming from Dr. Patterson or somewhere else? I just didn't know if that was.
Yeah, that's fine.
Okay, all right, I just didn't know if that was, like, if you're trying to enter a competition somewhere or something.
No, it's more of the criteria that would allow them to fit it in the window
Oh, okay,
and test it in the window.
okay, cool. You've done a lot of analysis on angle of attack, coefficient of lift, drag, et cetera. When you 3D print something, it's gonna have a rougher surface than if you have, a purely smooth, like, let's say, aluminum surface. Have you considered that at all in your model? Because you're doing a lot of your basis of what you're doing with coefficient of lift, coefficient of drag numbers. So thought about that at all in the process? I didn't hear any mention of that at the top.
We're planning on with the final model to sand the surfaces smoother.
Okay.
And then either fill them, or if the sanding alone gets them to be a smoother surface, we're thinking that will kind of offset that little bit of roughness that the 3D print originally has. Also, when we printing things too, we're trying to make sure that we print them in orientation that gives us the best surface. Because if you look at like the bottoms of the wings, this is how we originally was gonna print them. I mean, they're like, if you want to feel them, they're super smooth.
Yeah.
Some of the outputs of those.
Yeah.
Like,
Quite nice. Thank you. I think not just considerations of which side is going to be the smoothest. You have other considerations when it comes to printing orientation, which might be things like what?
filling and
Yeah.
fill and stuff.
Structure, and that would create more weight.
Right. So I didn't hear you talk much about, 3D prints, they have different properties in different directions, right? And so the orientation in which you print is going to end up being important. So that's one last thing, and then I'll hand it over. Is you're talking about different profiles that you selected. You had a NACA profile selector and et cetera, and you talked about one being optimized or not optimized. And my question is, what is your criteria for being optimized versus being not optimized? Is it lift to drag ratio? Is it purely the coefficient of lift? Like, what are you looking at?
For the actual like optimization, we were just to go through with the model and then run it through for the lift to drag ratio to try and get that the highest possible through CFD.
So that's your criteria for optimization is CL over CD, basically. Okay. Okay, I'm done.
Is there a reason that you only tested the loading on the wing with the forces distributed on the front of the wing? Because I would expect that the wing is actually going to bend not this way, but more this way.
It had freedom to move that way, so it was actually deforming, not just backwards with it. It was deflecting down.
No, I mean, so you only put, maybe I'm wrong, maybe I misunderstood, but it seemed like your loading was the drag force and not the lift force acting on it. And so my comment is more the lift force is what's going to cause it to bend more than the drag force based on the aspect ratio of the shape.
Yeah. Yes, you would be correct. I put all the force on the actual leading system, so it was distributed throughout that entire plane. It's
Okay.
like the entirety of it, so it wasn't just acting. So it was mostly the drag, not really the lift. So,
Okay.
yeah.
And then for the non-rosy CFD analyses, can you tell me more about it? I mean, like what? So many questions.
The settings I selected and fluid.
Yeah.
Well, we used K Omega as the viscous fluid model and SST system for that. And then set the external pressure at the back of the wind tunnel to 0 PSI or KPA, it wasn't fluent. And then set the front to 70 miles an hour, used a velocity inlet. So there was pushing through that enclosure that you saw on the screen.
Hmm.
I don't know if you wanna know, we set the,
No, we can talk about that later. The last one I had was how much of those drag measurements were because of that large C clamp that you had in the window?
we actually, calibrated based on that. We ran a whole round with just the clamp and the fixture in there. And we
Okay.
calibrated all our other data based on that.
I appreciate that you did that. Right.
We also made sure the wing was about as parallel to the surface as possible, mounted soundly too, so that the fall on.
Mhm.
His mount, as you can see on the plane, works very well for his control surfaces. Like these things were sitting there. They
I-
wouldn't really move around at all in the physical window.
I actually designed the mount too with that same shape that we used on all the control surfaces too, to try and reduce the drag on that in the wind tunnel.
Okay. Dr. Fleming's gonna ask.
So for your battery propulsion system, have you considered the battery weight in your calculations? Because you have to fly for 20 minutes.
We took a rough guess at the battery. I used kind of some of my previous knowledge of what size battery would probably work in this size plane. Then we looked up a measurement and added like 10% to it. And then we added that to our sizing chart. That comes into that 1,100 grams that we had for like a rough weight guess.
Okay.
The components, all just doing research, taking the weights from the website and then using the CAD modeling with PLA.
Okay. Yeah, because the battery can be fairly chunky.
Yeah, I think it was like 300 grams on its own, maybe.
Yeah,
Really,
by
that's,
itself, it was like 300 even more.
Yeah.
Depending where we went with the battery, we're looking at 3S, 4S, that type of thing.
Okay. And what kind of battery were you thinking?
probably like a lithium polymer.
Okay. Yeah, it makes more sense. The other thing I was gonna ask you about is for your 70, mile per hour limit, have you looked at how your propellers are gonna work at that? Because you have a whole bunch of different pitches. Are you sure you're gonna be able to reach that? I mean, it's not that fast, but for the small plane, are you sure your propulsion system's gonna be able to give you
Right.
that amount of thrust at that speed?
Right now, at that speed, we need, we're making 380 grams of thrust and we have, I think roughly 350 grams of drag. When we ended up doing estimates on the drag that the whole plane would have based on this surface. And then adding that to the wing surface drag, because this has the same kind of blunt body as this, to give us some rough estimates of what our drag might be at that speed. Right now, we're creating enough thrust to theoretically get to that speed.
So the one thing is maybe you might have to look into this, is there's gonna be a propeller efficiency curve. And as you get to higher speeds, it's gonna start dropping off based on the pitch and the angle of your propellers. So that might be something that if you're really close on that thrust in the static test, your dynamic test might actually drop off and not quite speed. So it's something to kind of consider.
Gonna move on to the next group, so.
Yeah.
Measure the speed.
No, that worked.
I circled some other stuff later on. Most of that other ticket scratch like that for me. Question about that.
Yeah, that was one right on the question.
Yeah, you need to plug in, yeah, there's an outlet right. Gonna take over the road, so that.
Oh, yeah.
Early guys not there.
Yeah.
Yeah, there's a.
So I don't know, the other group can ask questions, so. How does that say what their grades, right?
I know.
I was gonna ask on the center of gravity. You guys done any center of gravity calculations?
Using other roads now.
Yeah, we're gonna see your stuff. But that's boring.
I want to.
yeah, you're good. There.
Good afternoon. First, I would like to thank everyone for taking up part of their day to be here. My name is Brett Hanley. I'm a mechanical engineering major at MSOE. These are my teammates.
Joey Spankowski. I'm Ben Garvey.
And we did our project on a 3D printed model race car.
So just to start by defining the problem, it was a remote controlled 1/12 scale car must be designed to travel at 70 miles per hour and navigate a circular curve of radius 36 yards at that speed. Said car must be made with all 3D printed components except for the battery control system and critical drivetrain components. So once we define the problem, we wanted to break it down into like a more broken down form. So we broke it down into objectives and constraints. So the three objectives were the design should obtain a speed of 70 miles per hour, and it should be able to do that during the curve. It should also be able to do this like more than once, so not just crash and then we're screwed. But and then the three constraints were that it needs to not exceed the dimensions of a 1/12 scale car. It should be again made from all 3D printed components except the motor control system and drivetrain components. And then from our kit car, we determined that we can't use any of the plastic parts as the 3D printed components because they weren't 3D printed. They were injection molded, and obviously we wouldn't be 3D printing them, but we could use like screws or other metal components from it. So with that said, the first thing that we designed was the body of the car, and each of the group members designed at least two, with three of them kind of being the same general shape. So as you can see from the 6 designs, like design 1, 3, and 6 kind of all share a general shape, with design 3 being like kind of the base design. And then design 1 looked at changing it by adding curvature. And then design 6 looked at changing the rear spoiler to see how that would affect the aerodynamics. We ended up scrapping design 2 and 4. Those were more used as like a start to get familiar with just the 3D modeling, especially design 4. That was like our first one that we designed. It was just for us to get comfortable with like creating lofts and just the abstract geometry for the design. So in order to determine which design we wanted to go with, we did CFD analysis using the Rosie computer, which is the supercomputer here at MSOE, which used 4 GPUs and 24 core processors to run OpenForm CFD software. The wind tunnel would automatically scale the model down and put in the velocity once we put in an STL file of each geometry, and then also a Reynolds number. And to get this Reynolds number, we used the body width constraint, which was 7.3 inches as a characteristic length, and determined the Reynolds number of 354,000. So this is what the Rosie data looked like, and it gave us the general flow over each design. It gave us the results in the X drag, the Y lift, and the Z lateral movement, as well as the coefficient of pressure. And this is like what the actual pictures looked like. So over there is a streamline, and this is just the center of pressure. So that would be able to get us to do hand calcs and stuff like that for moments. But so this is what the first design looked like. Design 3, 5, and design 6. And then in order to kind of decide which one we wanted to go with, we did a trade-off study as well as just like a result comparison. So we looked at things like complexity, visual appearance, aerodynamics, and then 3D printability of the design. And with that, we determined that the winner would be design 1. So as well with the trade-off study, we saw that it was the second closest for the CFD analysis, as well as we just thought it like cosmetically looked the best. had clearance for wheels and other components on the front end where some of the other designs did not.
Right, so in addition to using the Rosie supercomputer, which was essentially automated for us, all we had to do was submit the STL and input a Reynolds number. I made my own wind tunnel in another CFD software, ANSYS Fluent. I did this mainly to cross-validate with the Rosie results and also to study the mid-turn effects of the drag force. As you can see, lower left, that's a picture of my domain. It's from another software called Space Claim. Wanted to set up the domain so that it would accurately give us an answer. We wanted to model it. So we have 11 car lengths going back from the nose of the car. You can see the car and the smaller green box. I use that as a body of influence in the software to refine the mesh a lot more around the car so we can accurately track what's going on. And with the domain, it also accurately accounts for the turbulent effects. At the end of the day, I got a drag force result on design 1, which was within 0.8 of a Newton in the X direction for drag. And I'll take that, being that close to a supercomputer using this laptop. So I think that's pretty close. I also found out in the Fluent model that the drag parallel to the flow increased by 40% in the turn. See in the lower right, I have a depiction of the path lines. Colors are meaningless. They're just there to visually differentiate the lines. So those are the path lines to give you an idea of what's happening. So you got a lot of flow impinging on the side of the car. So variable filleting the edges to smooth the lateral flows will be pursued. So this was a pretty open-ended problem. Not to knock on the other groups, but the Baja team is designing maybe one or a handful of components for a Baja car. Another team was going through the effects of a diffuser on an Audi. We essentially have to design a whole 12 scale car. So we started with the body, and just for some more direction, we kept going with the frame and the control arms. So first off, with the frame assembly, we have to design all this to be 3D printed. We're going to be using Prujas, which have a 7 by 7 inch work table. So as you can see, I have a split line on the frame. Each of those are 7-inch lengths, so it'll be 2 prints. I'm using a base thickness of 3/16 of an inch. I also have a 1/2-inch ribbing. On the ribbing, there are dovetails connecting the 2 pieces. Now we went with dovetails, and we're going to continue going with dovetails in the assembly as much as we can for the sake that we're not using additional hardware, which can create stress concentrations where you use it. And it also locates the parts to each other, and it's at the end of the day, it'll be a strong hold. In addition to the dovetails, we can also stake them. So after assembly, we could readily have a through hole going through each one and put a dowel through there. We could even 3D print the dowels. So that'll be 2 prints for the frame. Next, upper control arm. So you want to pass this around. So this is a control arm assembly from the kit car that we got. So we used that. We looked at that. We're like, what is the purpose and life of this thing? How can we design it? How can we improve it? So basically went through all the functions of that assembly. And our control arm assembly will have twice the suspension length of travel as that design, which is one of the market leaders in the 12 scale
RC cars. It's a lucrative business. So, and that's just for safety when we're going to be testing it on parking lots in Milwaukee. So we don't want it to bottom out the suspension as soon as it hits a little bump. In addition to the design, the FEA was conducted to simulate the loading the outboard control arm will experience at 70 miles per hour. So by outboard, I mean, those not familiar with naval terminology, as you're taking a turn, that's going to be, if you're turning left, it's going to be the right control arm, because that's where all the weight of the car is going to be, most of the weight of the car. So for loads and constraints of this FEA model, I applied factors of 5, 4, and 3 to the static corner weight of the car to account for possible impact loading in the Y, Z, and X direction per model. See that orientation for you. I also use displacement constraints in the X and Y directions on the dovetail faces. That is those guys here. And then I also have a zero displacement on the Z and the inboard face. With a mesh, I created a mesh of about 12,000 nodes and 7,000 elements. I did use refinements on 1/4 inch and 32nd inch corner radii. One thing you can do when you're using the FEA software, so we did apply the actual material PLA is what's coming out of the 3D printer. We applied that to our model, and you just look at the center of volume and the center of gravity before and after you applied the material. And as long as they're the same, I mean, these are pretty much, they're perpetually the same center of volume and gravity. That tells me that probably going to have a valid model and get good results. So I solved for equivalent stress and total deformation. We found from research earlier in the semester that 3D printed PLA has an ultimate tensile strength of about 7 KSI. So just for frame of reference, that's already about 1/6 of the strength that steel starts at. So observing the highest on average equivalent stress away from sharp corners, because when you're doing FEA, you're going to have theoretically infinite stress on a sharp corner. So you gotta, here I went and found, I probed the 30,000th corner that's down here on the dovetail. And I got 6.3 KSI, which has a 1.1 factor of safety. So another thing to validate the model is you can do a reaction forces check. So as long as the reaction forces equal the applied force, there's a good likelihood that you have an accurate simulation. And to further validate this FEA, we can test our actual 3D printed model. What we'll do is we'll keep the geometry the same and simplify the loading and the simulation. We can hang a weight on the upper ball joint location. So upper ball joint is the part that's in direct contact, that will be in direct contact with the control arm, and the force will be going through there. So we'll take the same location, that force will be acting, we'll hang a weight, and we'll change our simulation to reflect what that is, and then we can have a direct comparison of results with total deformation. We'll measure with an indicator where that ends up. So after conducting this simulation, some possible improvements that will be pursued is we can increase the leading dovetail cross section. That was the right around the area of the peak stress. And we can also use 3 dovetails instead of 2 to distribute more of that loading.
Okay, so next I'm gonna talk about the component selection. So we used matrices to decide on what parts we're gonna buy. And from this, we calculated the costs. We decided to stay on the cheaper side for most of the motors. So that's why they're mostly 4s and 5s. They range from like 80 to 200 for what we were working with. We prefer to be on the cheaper side so we can buy an extra one if it breaks. And then for the batteries, we ended up going with the 3S. That was the biggest impact we wanted. It had more power and it would allow us to run the motor, the radio transmitter, and the servo without taking too much power away from the motor itself. And so with that, it was a all or nothing scale for those. Either it allowed 3S batteries for that motor or it didn't. And then for ESC options, we had 5s were ones that came with the motor so that they worked together and there wasn't any tampering outside of the box. You could just plug it in and go with it. And then the rest were reviews or recommendations from hobbyists or forums about which ones would go good together. And then for torque and speed, those were just found on the specs sheet for those motors. And so they were easily just put into the table. And then finally, for the size, all of them are the same relatively, except for the Rocket, which is for a smaller model of car, which would have worked good in ours, but it had other drawbacks that made it so it didn't win. We had two-way tie for our top motor, and we ended up going with the Hobby Wing because it was a cheaper option. And then for wheels and tires, we had another 2 options because we were recommended a hard foam tire, which would crack and chip on pavement. And so we got an extra tire in case we wanted to test like smaller tests, like learn to drive the car without ruining all the tires. Moving on to the transmitter, everything's pretty self-explanatory with that one, except for the user interface. For the user interface, we wanted a simple controller that we could use and learn one without too many joysticks and all that. It's just kind of a standard toggle for the throttle and then a wheel to change the direction. And for servos, we went with the bottom option. It had the was one of the more expensive ones, but it had other benefits that outweighed the others. So far, we've purchased 2 batteries, a motor and ESC combo, wheels, a transmitter and receiver combo, a servo, and a kit car for reverse engineering. On the left, you can see the kit car that we built from the parts they sent us. While we're not able to use everything on the car, obviously, it's still great to work on it because none of us really have good experience with RC cars. And so it was great to have an example to work off of. And on the right is our current model of the car. As you can see, it's pretty different than what we bought for the test car. But it's still great to have the test car because, like I said, it was to learn. Here's our tentative budget. Most of what is on there is already bought, except for the suspension and the backup parts, which the backup parts are the Hobby Wing motor and ESC combo. We've got 2. We've got 1 right now. We have another one just in case things go bad. We've got more wheels in the future in case they break, and then an extra suspension and servo. Again, in case they break or we need to buy a new one because it doesn't fit. And then looking forward to next semester, we have a Gantt chart set up by weeks. So the first week we get back, we plan to work on the differential drive. We had one come with the kit, but it might not work with our model because it's slightly different. And so when we get back from break, we have to decide on whether or not to work with it or to buy another one and get it shipped as soon as possible. And then that brings us to week 2, where we want to finish all of the rear axle designs, get those modeled and CAD'd up so that we can move on to week 3 and finish all of our CAD, put the entire assembly together. And then week 4 to 8, we plan to print, said design and get it all assembled physically to test in the following 4 weeks to improve the car, get it working, making sure that it can actually pass the defined test. And then finally is the presentation prep, where we'll finalize the design and get it all ready for presentation. This is our reference for the ELA material products. Thank you.
May I?
Mhm.
Okay. So you had some initial designs that were up there, 6 of them that you showed, right? And then you like kind of crossed them out, went down to 4, et cetera. I think part of the design process is kind of understanding sort of state of the art, and there's this whole like, think of all the RC cars that like exist, right? And I think that might have been kind of missing from the presentation. I don't know if you had dug in on a lot of that RC car stuff or like seen a lot of the model race cars that already exist. But I would think that those initial first designs should have been based on maybe things that already exist. And it was unclear to me if that step had been taken. So can you appease me and say that you at least considered other designs before you just sort of put some stuff into CAD and then down selected to 4 from 6? Where these 6 even came from, I'm not sure.
Yeah, so the like initial like design, the 2 and the 4, especially the 4, and the like designs that we went with and kind of changed things. So we went like a pan kit car for the, because that's what we saw as like the most common 1/12 scale. And they kind of all had this like general like swooping shape like that. So that's what we like wanted to model. And then we wanted to see if changes that we came up with ourselves, like how that affected the aerodynamics. But yeah, it's like this one is like, especially like, we saw a lot of like this shape. So that's what we were trying to like
The
start with.
1980s Batmobile. No, I think it's like, once you have some designs, I think it's a good idea to maybe put them into CFD and figure out lift and drag. And I think all that is good. I just want to make sure that when you start with something, it's based on like some heritage. It's not, it just, I think I'm maybe missing the presentation. So good that you looked at it a little bit. Brent, you said that you're considering only using dovetails as a method for joining. Is that everywhere in the car, or just sort of that those 2 major pieces that are going to connect to each other?
I mainly was referring to the upper control arms, and also when we have a rear axle mounting scheme, we're gonna use those as well. It's gonna be dovetailed onto the frame
Okay.
that we showed.
So you got to get like your battery connected and, you know, some other like transmitter components connected. How are we attaching these? And are you just kind of using parts from the kit? Like, I mean, are you allowing adhesives? Are you allowing like glue and stuff?
Yeah.
Okay.
So we're actually trying to avoid adhesives in the assembly, because in case something does break, then if it's glued together, then we essentially have to reprint both things. Otherwise, we gotta break it. You know, it'll just be a little bit more, it'll be more replaceable for further testing. It also, coming from a machining and tool making background, if you feel like putting stuff together with glue isn't really a great way to go.
Yeah, I understand. Lastly is, you've got a lot of components that you're still thinking about including, I guess, some transmitters, some battery pack, I guess, or something. Are those going inside like the shape that you like prescribed here? Are they hanging off the side of the car? Because that's obviously going to affect the
If you go back, I got a few slides.
Yeah.
It's the assembly CAD view. Yeah, so like this is essentially everything that's going in there. There's gonna be a small transmitter relay. It's probably about 3/8 by 3/8 of an inch. I was mainly concerned about, these are the major components that are taking up all the space. And this is a frame. Now, the frame doesn't fill up the constraints of the 12 scale that we had, the length constraints, because we still need need room for the wheels and whatnot and the spindles out there. But this, for the most part, is going to be the major layout going forward. And once the layout is finalized, what we can do is include some snap straps that'll be printed essentially onto the frame. So one of the nice things about having all this 3D printed is if something just doesn't work, we can make a modification and reprint it right away.
All right, no,
I think Dr. Hart's concerned about the amount of time that it will take to make sure those dovetail joints work okay. And I get what you're saying about the glue, but to be honest, the glue is probably stronger than the PLA is. And so I wouldn't be scared or worried about using adhesives. I'd be more scared about designing parts that are too thin or not dense enough. But I was going to ask about the when you ran your CFD simulations, I didn't notice wheels on any of them. When you ran the Rosie simulations, what were the models that you submitted to Rosie?
Yeah, they were just without those. They were just like the shell.
Okay. So all those lift values will be only based on the downforce on top of the car, because it will have simulated it like there was no bottom of the car. So if you looked at the kind of downforce calculations that you need for the car successfully taking that rather quick corner.
So back in week 1, I did some physics 2, just verify that the car wasn't going to have a tendency to flip over in the turn. And just based off of the simple free body diagram, I determined that it was feasible without having any downforce. Also, if you have just the weight of the car holding it down.
Were you able to get any of that data, any of the lift data out of your fluence?
I did.
When it was turning the corner?
Yes, I actually did have a downforce. Did not include it on this presentation.
Yeah, this one does have wheels. I forgot it.
Yep, I ran my Fluent with wheels. And to actually make a direct comparison with Rosie, I did not use the 354,000 Reynolds. It's a little convoluted what the characteristic length used, that which one you should actually use for a shape like that. So if you take an average of the two lengths that are the front cross-sectional area, I got about 309,000 RE, and that's a number that I used, and I think that was closer to the RE that was actually in this simulation. That's where I got my result within 0.8 of a Newton of Rosie. If I recall correctly, I think I still had a negative downforce. I think it was something like negative 14 newtons in Y. So so there was downforce there. Having the wheels there and the CFD did not cause it to have any positive lift.
We can talk about the Reynolds number stuff later. But you guys want to go? Or no, you guys got to get out there because we're running a little late. Or you can ask the question as you said it. I love that.
yeah,
Yeah, we're just gonna put up questions. You guys will actually have time to ask questions, sure, but.
All right, so we say the best for last. We are another. I'm
Proclaim.
just trying to hype us up before the presentation. So my name is Jillian, and these are my team members, Jacob and John, and we also set out to design the 3D printed RC. So similar to the last group, we had another similar problem statement where we wanted to design a 3D printed RC car that could go 70 miles per hour through a 100-foot radius curve. That was calculated based off of Beats Field and using that just as the standard so that in a better case scenario, we can definitely handle it. We had similar design constraints and objectives as the other team, but some of ours that differed from the other team was that of our control system. We wanted to make sure that our control system could communicate with the car for a radius of 400 feet. That also being based off of Beats Field just for extra communication. And then we wanted to make sure that our car had good response time so that any one of us controlling the car could handle driving it. And then just mainly using 3D printed materials for our aerodynamic components. And again, achieving that 70 miles per hour through the curve. And we want that to be handled multiple times so that, again, our car doesn't break. We can complete a race and a lap through Beats Field.
So in order to verify that we could actually go around the 100-foot corner at 7 miles an hour, we had a free body diagram of how much downforce we would actually require to make that corner. So we first looked at the acceleration that is required to stay in the corner. So the car would be pulling 3.27 Gs in order to pull through the corner, which is a little bit over what F1 cars pull in a corner. So it's pretty high for what we're trying to shoot for. And then we started calculating the amount of downforce that would be required for this. And then using a 5-pound car would be an estimate of where it would be at. And we did 2 calculations based on 2 different surfaces, one for asphalt, one for turf, which would be for Beats Field. For asphalt, we used coefficient friction of 0.9, and the required downforce that would need would be 13 pounds. And then for turf, we would require 20 pounds of downforce. This would be all on top of that 5 pounds of legal weight. And then from this, we realized that we need to look into a lot of aerodynamic elements in order to actually achieve that downforce. So we started looking into front wings, rear wings, underbody flows, like Venturi tunnels in cars, like we're seeing in F1 in the 70s with a fan car style design. And then we also want to look at how all this goes together, like all these components work together in the main body.
So for initial concepting, we each came up with 3 different designs and then met as a group and narrowed them down to our 3 favorite designs that we thought would meet these requirements and had the aerodynamic capacity that we were looking for. So the first design was a ground effect car using a Venturi tunnel. It had open wheels, so that was the biggest difference between design 1 and design 3. Design 3 just had a closed wheel. And then design 2 was using the fan car concept and also had closed wheel. And then we rated each of these on specific parameters that we thought were important to our success. These really being based off of our downforce calculations and the capability that the car would have. So we weighted those each based off of their significance to the success of the design. Some other ones that we did not think were as important, but still needed to be considered was cost and power requirements, because in the end, these were things that we could make sacrifices for, but were still important to the overall design.
So the first design was designed by me. It was taking inspiration from Pikes Peak cars and F1, where it's an open wheel style front, using a bunch of aero on the front, rear, and underbody. Some strong points with this design were that its weight would be really low, since we don't have to have any fairings up front. Speed goes in hand with weight, where the lower your weight is, the less power requirements that you require for it. And that controllability was rated highly due to the front wing that could provide downforce on the front. Some weak points were its complexity with all the aerodynamic elements, having to figure out how they all work together and make it actually achieve our required downforce. And cost, which was also rated poorly due to the fact that since we have a bunch of aerodynamic elements on the body itself, we're limited on room for components inside. So we would have to pick much smaller components that can sometimes be more expensive.
The second design was the fan car design. I designed this one, and this design was primarily focused on providing the maximum amount of downforce, which would theoretically give us the ability to reach much higher speeds in the corners. However, when looking at a fan car, there's reasons why it was banned from F1 and other competitions. Primarily, how a fan car works, and the majority of its downforce is generated by a low pressure area on the bottom side of the car, which has ductings to a fan on the back of the car. So you suck the air out there and generate a low pressure zone underneath the car, which sort of sucks it to the ground. The problem with that is if you have any sort of damage to your side skirts, or you hit a bump, or you hit anything and the front of the car lifts up at all, well, you've just lost all your downforce. You're doing that with a car that's 12 scale at 70 mile an hour corner, and we hit a rock and we lose all of our downforce. It's basically completely uncontrollable. And that's the reason why it's banned in actual F1, hill climbing, and other full-size competitions. So that was the main weak point of this design. Also, you have to include a higher cost with new electrical components that would not be in the other designs. And then the complexity of that ducting and airflow underneath that car was another weak point.
So this last design was designed by me. We thought some of the strong points were it was a lot simpler than the first design. It had similar components, but it didn't require as many individual components, which would be easier for us in the long run of if something breaks, there's just one component to swap out versus multiple. The problems were the aerodynamics were completely off. And then on top of that, vehicle weight and speed were just not as optimized as the first design. So it was just something to weigh whether we wanted an optimized design or a simpler swap out in case something breaks.
Another thing that we also looked at besides just aero would be the driveline type. We looked at 3 different types: 4-wheel drive, all-wheel drive, and rear-wheel drive. Some of the main points were that 4-wheel drive or all-wheel drive would help with controllability on a 1/12 scale. From my experience with driving RC cars, rear-wheel drive is very uncontrollable, especially at high speeds. So as soon as you go slide out into a corner or get any wheel slip, you just spin down. It's so hard to control just due to the size of it. It just spins really easily. So we wanted to go with four-wheel drive option, even though it would increase our weight. And then between four-wheel drive and all-wheel drive, what we wanted to go with would actually be all-wheel drive due to the addition of a center diff, which would allow for different wheel speeds, which would help with cornering.
From all of these, we decided to go with our first design. And we did sort of based off an F1 car with over exaggerated hill climb style aerodynamic elements. You watch a hill climb race, they have massive rear wings, front wings, so on and so forth. So we sort of mesh those two together. We plan to utilize an underbody Venturi tunnel, a very large front and rear wing to generate the majority of our downforce. And we originally designed this to be an open wheel design. However, this was iterated upon and changed to closed wheel design. Just restating the parameters that we selected for this design, we primarily chose it for its ability to have high speed, high controllability, very feasible, and it just wasn't the most complex overall in terms of the. It was the most controllable and it had the lowest weight. My bad. It was relatively complex for its aerodynamic interactions with each other, but it would have the highest speed, controllability, and lowest weight. And then we designed a very basic, just baseline model for this car. We didn't include any of the major aerodynamic elements. We don't have a front wing, back wing, or rear underbody. This was just to establish a baseline that we could attach different components to. For example, if you want to test our rear wing, our front wing, or underbodies individually, and then or possibly all together, just to establish a baseline that we could test further iterations and compare them to.
Now, using that baseline body and then iterating through, the different things and whatnot, we ended up coming with this design here, which is actually similar to what we have printed here, except that small front wing is removed, but that, we'll talk about that later. So iterating through, we wanted to add a functional front and rear wing, just because that initial design did not have any of that. It's just kind of a wedge up front, which was not using any actual airfoils. So started using multiple different airfoils here, made the Venturi tunnel a little bit more realistic to what would be on the vehicle, and added the rear wing with multiple elements. So for the front wing on that car, we chose the Epler E71. The reason we chose this is due to its low Reynolds numbers that it's very efficient at. Most airfoils, like at low Reynolds numbers, like 100,000 to 50,000, you can start seeing stall on it, like at high angles of attack, which is not ideal because then we start losing downforce. So especially for the front wing, the flow is very uniform to begin with. So all the way through the core length of the airfoil, it will be relatively linear. So we want to have it at that really low Reynolds numbers. Oh yeah, take the model.
Yeah, take a look.
Yeah, so using the figure plot from Airfoil Tools, we wanted to shoot around like a 5 to 10 degree angle of attack for the front wing, just to keep our highest coefficient of lift. And then, yeah, this front wing is also a ground effect as well, which helps add into the additional lift. Then the underbody, this is kind of the shape of the Venturi tunnel that we have here. So it just basically goes from the free stream, kind of goes down to a small area and then expands out. The expansion that we chose was a 14 degree. Reason why we chose 14 was because from what we're looking at in research, angles between 10 to 14 gave the most optimal pressure differential, while also not having any flow separation, which would, decrease the effect of the Venturi tunnel.
Now, looking at the back wing, several different sources were analyzed to just figure out what the general shape of this back wing would be. And looking at the specific airfoil we decided to use, we decided to use an S123 airfoil. This airfoil is renowned among hobbyists for its ability to generate high lift, low drag, and low Reynolds numbers. And using airfoil tool, we were able to determine the angle of attack. We chose approximately 12 degrees for our angle of attack. That's where we found we could get the highest coefficient of lift without introducing too much drag. This is just one of the plots that we used, but we found that 12 degrees was the best area for angle attack. From running just that rear wing, that our dual element side plate rear wing, we found a downforce of 3.8 pounds for just the rear wing on its own, not including its interaction with the rest of the car. And it's a very low drag force of 1.1 pounds. So we had a very substantial lift to drag ratio. And then we also looked at the feasibility of a second wing. This wing, utilizing the S9104 airfoils, that airfoil is specifically known to be a slight improvement over the S1223 airfoil, which we used previously. The idea is that it generates more downforce while generating less drag. We then ran a rear wing through the Rosie wind tunnel with the same angle attack, same end plates, just so that we can compare the two. We found out that surprisingly, this wing actually generated less downforce while generating higher drag. So this was something we wanted to take a look into later, which we'll see later on.
So after running the individual wings, we obviously wanted to see how this affected the full body aerodynamics as well. Based off of the individual wing analysis, we assumed that the S1223 was going to do better because it did better on its own. It generated more downforce. So when we ran it attached to the full body with the front wing, we found that it had just over 11 pounds of downforce and just over 3 pounds of drag force. But when we ran the S9104, we actually found that it had more downforce and drag force than the other design. The downforce being really close to 12, and since we were shooting for 13 pounds of downforce for the asphalt, race runway, I guess, whatever you want to call it, that was a lot closer, and so we actually decided to go with the S9104 wing design because it was more applicable to what we needed for the full body aerodynamics. And then we printed out the design to test in the wind tunnel in SG01. We did have to remove the secondary front wing just because of printing right now. That's something that we're going to investigate later on. It was a little too thin to print out successfully. And then due to the printing beds, we had to split it into 3 different parts. So we split it obviously in half where the 2 different colors are. And then the wing is the last part, and we just attached it with glue.
So using that physical model, we went and tested it in the physical wind tunnel. We cannot really measure downforce due to the current setup that we have, so we can only really measure drag. And how we're doing that was the vehicle would be stuck on a sled, and that sled had like linear bearings on it and attached to a string to basically be pulling weight off of the scale, measuring drag that way. Not ideal, but that's kind of what we were at the point with it at this moment. And yeah, we measured flow velocity in the wind tunnel based off, the pitot stack tube, and basically changed that all the way from, I believe, 12 meters per second all the way to like 26. And these are the results that we got from the physical testing. So we went at a low speed, ramped up, and then came back down to see any hysteresis in our readings. And from the figure there, we have quite a bit, which is not great. We're likely seeing this due to the static friction in the bearings. It's not very smooth action. So when it gets to the higher drag, it probably pulls further out, and then the friction in the bearings doesn't want to come back. So we started having residual drag force, which is not real. So we wanted to try and compare some of these results, even though they may not be the best. So we chose a point at around 24 meters per second, and verify that with Rosie. So for drag, using the Rosie simulation, we had 8.75. And for the wind tunnel, we had less than half of that, 3.42, for a percent difference of like 87.6%, which is not great. We can't really verify anything with that reading. So that's something we'll have to look into later on for the next semester to actually get an actual verification, validation from our simulation and physical testing.
Now, looking at our parts, we spent the majority of our cost with the wheels, telemetry control, and the motors. This was because we wanted to get the highest quality for motors, our telemetry and controls, just because we're operating such high speed, we prioritize those. And we put together a part list with a bunch of researching. We have individual specific components and brands we've taken a look at, and we just sort of went through and determined which ones would be the best for those. This all resulted in us not exceeding the $1,000 grant we received from the ME department, which was a big, really good for us because we're expected to maybe break like a component or two, and we actually built in a little bit of money for the spare parts. So we hit the limit, but we have not exceeded it, which is very beneficial. Next, in terms of iterating the design in the next semester and improving it, one of the things we plan to focus on is more aerodynamic improvements. First off, we are seeing about 12 pounds of downforce. We want to reach 13 for the turf, 13 for the asphalt, and 20 for the turf. We're going to do this by increasing downforce from the back wing and the venturi tunnel, and then overall optimizing the flow over the top of the car and the interaction between different components. And something we did while designing aerodynamics is to sort of use an idealized material. We wouldn't expect it to break or experience any sort of detrimental stress concentrations. So we still need to run an FEA on the wings. However, when we ran our idealized material through the wind tunnel, which reached 26 meters per second, approximately 64 miles an hour, really close to our 7-mile-an-hour goal, we did not experience any sort of breakage, bending, stressing. So while we still need to run an FEA, we don't anticipate seeing any sort of detrimental problems in the future for our aerodynamics. Then we need to model all the individual drivetrain, suspension, and other interior components to make sure that they fit within inside our physical model that we've generated so far. Iterations we will make on it. Finally, once we've made sure that all of our components fit in our current model, and then whatever change we make to it, we plan to test it, tune it, and then race it. Here is a Gantt chart laying out all those different things we discussed. We plan on finishing up our car around the end of March in terms of printing it and attaching all the components, giving us a significant amount of time, very significant amount of time to test, tune, and make sure that we've reached our goal. And anything that may happen during that tuning, such as we break something, or we need to make sure that we need improved downforce. We just want to give ourselves the maximum amount of time that we can make those changes. That would be very critical to the overall success of our project. Finally, here are our sources. Any questions?
Good job, guys. At the very beginning, you talked about the required downforce that you needed to keep this thing from slipping, essentially. And, you know, you're not on a banked surface, I
No.
assume, right?
Just assuming it's
Flat ground.
Yeah.
And so here you've got asphalt and, you know, a nice coefficient of friction between, I assume, rubber wheels and the asphalt.
Yeah, we couldn't find the exact coefficient of friction for like RC car tires.
You know, good enough. Yes, you gotta make some number, right?
Yeah.
And here you find 13.2 pounds, right? And then you go to the CFD a little bit later and you find that your downforce is 11.7.
Yeah.
Yeah, so
Not
that's
quite hitting that, a little uncomfortable.
yeah.
Talk about that.
So we are planning on doing iterations, primarily when it comes to the rear wing. Like we said earlier, we had a version that should be better, but it wasn't when we tested with the body. So we spend a lot of time looking at the overall aerodynamic interaction between the components. And we believe that utilizing a different rear wing or just changing it, we can easily make up for that difference, because we are seeing large changes from our baseline model in just adding more aerodynamic components or lengthening the front wing. We have plans for that. It is not lost on us. We haven't reached that 13 pounds or that 20 pounds for that turf, but we don't expect that to be a limiting factor.
Yeah, one thing about your project in particular is that you're just trying to hit like some top speed of 70 miles per hour.
Oh,
Right.
no, that's through the corner.
Through the
That's-
corner.
Yeah,
Um,
that's the hard part.
Yeah,
It's, I mean, no problem, drop it off.
but you have some like balance between, okay, if your car is a brick, it's not gonna slide, right? But you have to get to the 70 miles an hour, right?
Yeah.
So you wanna lightweight it, but when you lightweight it, it's more likely to slip. And I didn't really hear a lot of discussion about how much this is actually gonna weigh. You assumed 5 pounds, but is that really what it's gonna weigh? And-
No, yeah, we still have yet to purchase any components and weigh them out physically. That's just a rough guess. Like I've had experience with RC cars and know roughly the weight of the components and batteries.
Yeah,
It's just a ballpark right now, or like a goal what we want to shoot for.
yeah.
Yeah.
I think what you've done so far is really awesome. Don't get me wrong. I'm not trying to like, you know, yuck your yum or whatever, but you spent a lot of time on like the aerodynamics, but I think it's great. I think it's really smart use of the time. But there's some design decisions that I think might influence some of this shape, like the weight, and for instance, that you're spending a lot of time on how much downforce can we get, but maybe you're not quite accurate on all your weights, and so maybe the number that you're shooting for isn't quite right, and so maybe getting really heavy into the weeds before you've made some larger decisions that are gonna influence the
Yeah.
final result. I'm just worried about that slightly.
We
Yeah.
did, when making our components list, make sure that we were considering the weight of each component on the website. Obviously not the best thing
Sure.
to be using, but we were using that, especially, I believe it 11, I don't remember when we were 10 or 11 was when we were doing this, and then we were using that to modify the biggest. Obviously, the first design that we showed you looks nothing like
Sure.
this design. That's where that big change really came in, is when we started making components lists and started evaluating them.
Cool.
So it was not an afterthought, but it wasn't the primary focus of what we were doing, but we did consider it as we were taking steps to do it.
Last comment is, like, you have a build direction, obviously, for the 3D print. I mean, you're restricted by, like, you built this in a vertical orientation, right? I see that you built this on this direction. You know, and they have different strengths in different directions, and so you should really think when you're actually building what the orientation of this is gonna be, maybe you wanna start thinking about how it's gonna be loaded, and one direction's more gonna be more loaded than the other. I think this probably is the right way to build this component, but that's different than how you build these components.
Yeah.
It's something we'll have to look into when we're actually like slicing jobs.
Yeah.
Which gives us like the
I'm not
best
sure.
adhesion.
I don't know if I necessarily have an intuition which is good or bad or right or wrong
Yes.
at this moment, but just be confident.
Yeah.
But really cool. I like to see them all. It's really nice. Thank you.
And also, when we finally got into the wind tunnel, like right at the end, and ran our physical model through there, we ran at a very respectable, like, fraction of the speed we're gonna run it at.
Oh.
Didn't see any failures.
We got up to like 60 something,
Yeah,
but like it's not in the optimal pot or spot in the wind tunnel where
Yeah.
all the areas, laminar, right? It's on the edge where like boundary layers build up and all that. It's not ideal at the moment.
So about the wind tunnel, like typically I've seen like it has the boundary dish on the back that you fasten it to so that it sits kind of in the middle. of the
Yeah,
tunnel.
that's
We
what
do not
I
have
want.
that. I haven't used it with them, though.
But like,
So 6x6 load cells.
Yeah.
I got a price quote on them, 10 grand.
Okay.
Minimum quantity of 10.
Oh, yeah, okay.
So
granted,
it was either wait for somebody else to order them and then like piggyback, which they said for this range that we're looking at,
Okay.
they do it so rarely that they had no idea when.
Okay, yeah, I was just curious. I've never used the wind tunnel downstairs. So.
And I'm 3D printing a third version of one that I'm making myself.
Okay,
Yeah, you just can't afford. So with the weight, so just so I understand correctly, with the weight, you would be over the downforce that you need or not?
no, we're about a pound short for like asphalt.
So you had added approximate weight to your downforce?
No,
Or would,
yeah, so
Where did you
based
come
on
from?
the calculation. So basically, it's the weight minus.
okay, I see.
Yeah.
Yeah, I get it. Like you missed an opportunity if you go to your last.
Man, you're in the cycle of this life.
No, there you go. You could have, I saw you guys spamming the wind tunnel, which is great, but you could have done those points and put the rosy ones on there too.
Yeah.
Yeah.
Missed opportunity. But otherwise,
Yeah, those points banged were actually for CFD project that I had, and I was actually looking into Venturi tunnel optimization. We can include that in here. But with that, we actually had a difference between like ANSYS results and rosy results, and I think it's due to like flow separation that I'm seeing in ANSYS, but not with rosy. So that may be where we're seeing like a big difference, but like the trend line was similar between the two, but.
interesting.
Yeah, flow separation might be a thing here too, which causes a big difference because again, this is a rough surface or rougher. than
Yeah,
what
and like that
rosy is.
14-degree for the diffuser may be too big, man, so we go down to like 10.
Well, and that's like on a sled.
Yeah.
It's like hovering above the bottom surface. There's a lot of.
Yeah, there's a lot of obstacles that.
Yeah, a lot of
Yeah, good job. Yeah, good
Yeah,
job.
cool.
Thank you.
All right, good job, guys.
All right, it's been break.
You never know.
You see the.
But